So in the previous session we discussed about the program counter and the stack pointer. Program counter basically points and keeps track of the instruction address of the instruction from where it can be executed, while the stack pointer basically keeps track of the stack memory. Stack memory is basically used for modular programming. That means in case we need to call an interrupt or run a program within another program, subroutine within a routine. So there, in such cases, we go for stack pointer. So one more register that we need to discuss is the instruction register. So it's again an 8-bit register represented by IR, and it's an inaccessible register. That means the programmer, the user, cannot basically modify the contents or read the contents of this register. So it's again an important registry in 8085, and it basically is the destination for the opcode. So all opcodes, that means basically the instruction itself that needs to be defined, will be placed in the instruction register, and status signals are basically issued by the microprocessor at the start of the execution of the program. And in the very first state, in the T1 state of the microprocessor, the opcode is basically the opcode fetch machine cycle is basically the first machine cycle of any instruction, and in its T1 state, that is the first state of the microprocessor, the instruction register will be loaded with the instruction that is basically obtained from the memory of the microprocessor. Fine. Not in the T1 state, in the first machine cycle. So in the first machine cycle, that is opcode fetch machine cycle, in most of the cases, in all the instructions, the first machine cycle will be the opcode fetch machine cycle. So what happens in this case is that in its T2 state, in the T1 state, the address lines will be, since we know that there are bidirectional, there are 8 bits of 8 bits AD0 to AD7 that are used for both address as well as data. So in T1 state, that will be used to carry the data, but in T2 state, once the address lines are free from the memory, the opcode will be fetched onto the data lines, now data bus rather, AD0 to AD7, and in T3 state, the instruction register will be fed with the data that's carried by the data bus. So once the instruction register is basically fed, then only the microprocessor will be able to understand which instruction it needs to process, and accordingly the microprocessor will decide whether it's a read operation, a write operation. So status signals will be issued by the microprocessor based upon this instruction register. As we have discussed, you have two status signals, S0 and S1. So for memory, for opcode fetch machine cycle, S1 and S0 both will be equal to 1, while as IO will be equal to 0. So we have discussed this status signals. In case of write operation, S1 will be 0, S0 will be 1. In case of read operation, S1 will be 1 and S0 will be 0. So that we have actually already discussed previously also. So instruction register, simply it carries the opcode. Opcode is basically what will define our instruction. Say for example, we are defining an instruction move A 50H. Fine. So this is an instruction. So this opcode, the opcode of this particular instruction, that will be basically a hexadecimal equivalent. Fine. So you will need to know that from the you'll be basically provided with a chart from where you can basically find out the equivalent of this instruction. So you'll be basically feeding the hexadecimals in the memory of the microprocessor, and accordingly the microprocessor will be able to understand whether this is a data or whether this is an instruction by looking at the hexadecimal number that you feed. So in the instruction register, the opcodes are basically it's basically a destination for the opcode from where basically instruction can be defined for the microprocessor. So we have discussed the different components. We discussed the ALU unit. We discussed the general purpose registers. Third we'll be discussing the timing and control unit. So this unit will basically be involved with the setting the clock cycle as well as the clock frequency of the microprocessor 8085, as well as deciding about various control sequences that will be executed by the microprocessor, certain status serial operations that are basically executed by the microprocessor. Fine. So we have read instructions, write instructions, interrupt acknowledge instructions that will be basically decided using the control signals. So there are a number of control signals. You have read, you have write, and you have interrupt acknowledge. So in the pin diagram also, when we were discussing the pin diagram, we discussed a little bit about these instructions and how they are active low state, and therefore in the T reset state these signals will be tri-stated, but in the T2 state the read instruction will become active low, so that it basically starts the operation of execution. In T3 state of the opcode fetch machine cycle, the microprocessor basically reads the opcode that we discussed in case of the instruction register, and that will be actually placed in the instruction register, and from the opcode goes to the decoder, where the opcode is decoded in the T4 state of the opcode fetch machine cycle. Fine. In the T3 state, the opcode is basically read and by the microprocessor and stored in the instruction register, and in the T4 state the opcode then goes to the decoder, where the opcode is decoded for the microprocessor to process that information and to start execution. Various control signals will be the control and timing unit basically will be controlling and monitoring different operations. One will be the serial operation, the timing operation, read instructions, write operations. So for different machine cycles, we'll be having different states of these pins. Fine. So you have pin IO by M bar, S1 and S2. We have defined these pins. So for different machine cycles, say for example for memory read machine cycle, IO will be 0, S1 will be 1, and S0 will be 0. For memory write machine cycle, IO will be 0, S1 will be 0, and S1 will be 0 and S0 will be equal to 1. Fine. As well as read instruction, in this case we talk about read. read will be also 0 because it is active low. Write will be 1, it is at high state. It will not be active. Since this is a memory read machine cycle, read instruction will be active, write instruction will not be active, as well as INTA will be 1. Again, since it is at high state, it will be inactive. Memory write machine cycle, for that case this will be 1, 0, and this will again be 1. So memory read machine cycle, in this machine cycle the microprocessor basically reads the data from the memory. Status of different pins of the microprocessor will be monitored by the timing and control unit, and you can basically see that in these two machine cycles that we have defined, memory read and memory write machine cycle, the status of these pins will be as such. Fine. Similarly, we have then IO read and IO write machine cycle. IO read machine cycle and IO write machine cycle. So for IO read and IO write, these two will be 1. S1 is 1 for read, S0 is 0 for read, S1 is 0 for write, S0 is 1 for write. Read will be 0 here because this is a read cycle and it is active low. Write will be 1. This is not an interrupt, so this will still be 1. Read will be 1 in case of a write. This will be 0 and this will be again 1. So you can basically distinguish between different machine cycles, what will be the status of different pins of the microprocessor set by the that's actually monitored by the timing and control unit of the microprocessor. So these will be the values of different pins of the microprocessor. So we still have two more components of the microprocessor. Regarding the architecture of the microprocessor, there is the interrupt control unit and the serial IO unit. These two will be discussed at a later stage, but for now we'll be basically now drawing the architecture, the block diagram of the microprocessor 8085. So this here represents symbolically an 8-bit internal data bus of the microprocessor. We know by now that the data bus is 8-bit. Fine. So with this data bus, basically both the interrupt control as well as the serial control units, serial IO control unit will be basically interfaced with this 8-bit internal data bus. We have the ALU unit. The ALU consists of accumulator. It's an 8-bit register. Fine. It consists of the temporary register, it consists of flag registers, and it consists of the ALU unit itself. So these arrows are very important. Accumulator is both reading onto the data bus as well as writing, reading from the data bus as well as writing onto the data bus. The temporary register is only able to read from the data bus, it will not be able to write onto the data bus. Flag register, it is bidirectional, that means it will be read as well as write. Flag register and ALU is both read write. Accumulator and ALU is only a one-way operation, and ALU then will basically be monitoring onto the data bus whatever will be processed. So this component this here basically represents your ALU unit. Fine. Next is your registers that we have discussed, the general purpose registers. Again, the general purpose registers will be bidirectional, that means they can access the data bus as well as write onto the data bus. There are two registers, W and Z, that can be actually also used as these registers can also be used as pairs, W, Z, B, C, D, E, H, L. They are individually 8 bus registers. As a pair you can form a combination of 16-bit register pairs. Fine. And then you have 16-bit registers, stack pointer, program counter, and ALR. This is your stack pointer, program counter, and ALR. All three of them are 16-bit registers. So they will be connected with an address buffer. Through an address buffer they will be basically communicating with the address lines of the microprocessor A8 to A15, as well as they will be connected with the data oblique address buffer, and through this data address oblique buffer they will be communicating with AD0 to AD7. AD0 to AD7 are bidirectional buses. They are multi-purpose buses. They are used for both address as well as data bus. So this is your general purpose section. Then we have discussed the instruction register. So instruction register basically will fetch the opcode from the data bus. That opcode will basically contain the information of the instruction that needs to be executed, and from the instruction register the opcode basically travels to the instruction decoder. Fine. And machine cycle encoder. So once the instruction is decoded, we can also decide what will be the next machine cycle of the microprocessor. And once the instruction register basically operates, it will set out the timing and control unit into action, or rather it will basically be interfaced with the timing and control unit, and it will basically set the status of various signals of the microprocessor. So timing and control unit will consist of number of signals. So we have firstly X1 and X2. X1 and X2, as I said to you earlier also, the oscillator is connected to X1 and X2 pins of the microprocessor for setting the clock frequency of this microprocessor. We have discussed about clock out, how an external device can be interfaced using clock out. There will be the ready signal, there will be read, write, address latch enable will also be monitored by the timing and control unit. You have SO, SI, and IO by M. Fine. As well as hold, hold HLDA, hold will be so these arrows are very important. The timing and control unit will set the status of some of these units, and some of the units externally will be monitoring, will be feeding the timing and control unit, and accordingly decide the next operation. You have reset in and you have reset out. And we have also discussed some other pins of the microprocessor, like there was INTR, there was INTA, there was RST 7.5, 6.5, RST 6.5, RST 5.5, and trap. So these are all actually interrupts that we'll be discussing in a later time. And in case of serial operation, we have discussed two pins, SID and SOD. So this here now represents your complete block diagram or the architecture of microprocessor 8085. We have studied the ALU unit, the general purpose registers, and the control unit of this microprocessor. We understand what will be the status of certain control signals. Some signals are still pending that we'll be discussing with some instructions that we'll be studying at a later stage. The interrupt and the serial control units at this stage are still not discussed yet. That interrupts we'll be discussing at a much later stage. So this here is your 8085 architecture. The most important registers have been signified. Almost everything is important, but the accumulator, the flag registers, and these general purpose registers, they all are important, but definitely accumulator is the most important. And everything here has a purpose. The registers serve their purpose of as an internal memory of the microprocessor. The ALU units basically will carry out the ALU operation of the microprocessor. So having done this, now we can basically start discussing about the instructions of the microprocessor. So we'll start with the addressing first, and then the instructions, the macro RTL of the instructions, and then the instructions themselves in the next session.